In one of the previous modules, we had learnt that friction is a resistive force that opposes motion. So I had taken the example of a chair, and again I can take the example of, let's say, this duster here. And if I try to push this duster in one direction, I see that after I give it a slight bit of push, it stops itself. And the reason that it stops is not due to its own tendency to stop, but it stops due to the force of friction. Friction is something that opposes motion. In this video, we will learn the mechanism behind the working of friction, or in other words, how friction works and what friction is exactly at a deeper level. So if we start, first of all, in what cases is friction present? Well, we know that for friction to be present, two objects have to be in contact with each other. So in this case, I had a duster that was in contact with the table. So this surface of the duster is in contact with the surface of the table, and only in that case do I get friction. If I lift it up, it is much easier to move it forwards and backwards, because there's no friction when there's no contact. So firstly, I need a contact for friction to occur. Now if I look closely at the surface of the duster, so even if you try to feel any surface around you, it might feel that it is smooth, but actually at the molecular level, if we zoom into the surface, we will see that this surface is not very smooth. So what I can do is I can draw the surface of this duster here, and let's see how it will look if we zoom into this duster quite a bit. So you see, if you look from the camera, that perspective, it looks pretty smooth, and when I feel it, it feels pretty smooth. Even the surface of the table feels very smooth, but actually at the molecular level, at a very deep, at a very small level, the table is not very smooth. If we look at the table at a very small level, at a very zoomed in level, then we'll see that the surface of the table is actually rough. So you can draw the surface of the table in somewhat this manner. Obviously this looks very different from the surface of a table. That is because I have zoomed into the surface quite a bit. So see, let's say I take this surface. So when you see it from that perspective, it looks smooth. But if you zoom into the surface, and if you keep on zooming into, you will see that there will be many irregularities or roughness on the surface of this duster, and that can be drawn like this. So here in red color, I have drawn the surface of the table, this table here, and I'll take another color, black, to draw the surface of the duster. Now again, the surface of the duster is not perfectly smooth, it is rough. So again, it has these irregularities or roughness. Okay, so I'll just complete the complete drawing, and let's say this is the remaining duster that I have. See, that's my duster, and here I have the surface of the table. Okay, and it has regular. So these two are the irregular surfaces, and keep in mind, everything around you is irregular to different extents. So the table is not so rough as compared to, let's say, the road. The road is very rough, or maybe a playground, it will be even more rough. So different surfaces have different amounts of different extent of roughness, but everything is rough, nothing is perfectly smooth. And so these are the roughness, this is the roughness or the irregularities of the surface. Now what happens is, when these two objects come into contact, these roughness, these irregularities actually interlock. So see, there are some projections outwards, so they are like my fingers, right? They are projecting out of the surface, and there are some projections, irregularities, from the other side of the other object. So what happens is, when you place these two objects on top of each other, they interlock just like this. And now if you can see, now if I try to move this in this direction, see, when it is not interlocked, then I can move them easily, right? The relative motion is easy. But when I lock them, when I place them on top of each other, they get locked, and now it is very difficult for me to move, and I have to overcome this interlocking to be able to move the object. So what happens is, these two irregularities actually end up interlocking. So let me just quickly draw one of the surface, and if I place the other object on top of it, what I get is I get this kind of interlocking. See the grooves, right, and these projections, they fit into each other, and this causes friction. So what happens now, if I push this object in this direction, so these projections that have been interlocked will try to resist the motion, and I'll have to apply a large amount of force, or a higher amount of force, to overcome these restrictions due to the interlocking of these projections. And when I overcome that interlocking, only then can I move the object in that direction. Once I stop this force from being applied, when I stop applying this force, this interlocking again tries to slow down the object, and that is why objects like this duster stops. See, it will stop on itself due to friction. And this interlocking mechanism is what causes friction, and due to this interlocking, friction occurs and objects slow down. And that's why some of you were asking me that if I apply some force less than the frictional force, will I get a motion in the opposite direction? Well, no. You can see from this mechanism itself that friction cannot cause any motion on its own. All friction can do is resist motion. So this interlocking can only resist motion, it will oppose motion, but it cannot bring something into motion. So this interlocking mechanism is what actually makes friction work. So that is the basic mechanism behind friction, and I hope this is clear to you. If you have any doubts regarding this mechanism or anything, you may ask me. That's it for this video.